Okay, let's get started. Looks like people are starting to trickle in here. So welcome to today's webinar on water in mining, monitoring, and design reconciliation. We've got our panel of experts here today, who I will formally introduce in just a moment. But before I do that, just give you a little bit of background of the Geotechnical Center of Excellence, who is putting on this webinar today. So we are at the University of Arizona. We're part of the School of Mining and Mineral Resources. We are an industry-funded group, and we are member-led. We are an interdisciplinary center, so we bring together a lot of disciplines to conduct collaborative geotechnical research and education as well. And education, this webinar is part of that, a piece of the charter. We also pride ourselves on bridging gaps within and between academia, industry, and other fields of study. So today's webinar is based on our professional development course, Water in Mine Operations and Slope Stability. This is an online and on-demand course. It is currently going on. You can find out more in the, if you click on the QR code there. I believe one of my trusty co-hosts will also put a link in the chat for you if you're interested in that. Today's course was developed in partnership with Patoa Associates and the Large Open Pit Project. So we want to give a huge shout out to both of them. It's a huge endeavor putting these courses together. We couldn't do it without their assistance and guidance. So we really, really want to thank them. As I mentioned, the GCE is a member-funded and member-led company. So I want to give a huge shout out to our member companies shown here. If you are watching today and you do not see your company there, you think you should be there, you'd like to be there, please contact us. You can contact any of us at the GCE, or you can send an email to gce@arizona.edu. We'd love to start that conversation with you. Okay, so now let's get into a couple of introductions, starting with the GCE webinar team. My name is James McNabb. I'm a senior research and development engineer here at the GCE. I'll be your main moderator today. I've got my trusty co-hosts, Allison Brucey. She's our program coordinator. Thanks for joining, Allison.
Thanks, James. Thank you, everybody, for being here today.
Next, we have Yash Sihag. He is one of our undergraduate research assistants. Thanks for joining, Yash.
Hello, everyone. Welcome.
And next, we have Greatness Ojim. She is another one of our undergraduate research assistants. Thanks for joining, Greatness.
Hello, everyone. Thank you for joining today.
Okay, let's get into our expert panel. First, we have Jeff Beal. He's a global technical advisor with Patoa Associates. Hello, Jeff. Thanks for joining.
Thanks, guys. Hope you enjoy the session. Good to be here.
Next, we have Jeremy Dowling. He is a hydrogeology advisor and president of Patoa Associates. Hello, Jeremy. Thanks for being here.
Yeah. Hi, everyone. Nice to be here.
Next, we have Jim Weigel. He's a principal hydrogeologist with Rio Tinto Kennecott. Hello, Jim.
Hello. Welcome, everybody.
Next, we have Blair Douglas. He's a global practice lead of hydrogeology and water management with BHP Resource Center of Excellence. Hello, Blair. Thanks for joining.
Hello. Thank you.
All right, next we have Ian Callow. He's a principal hydrogeologist with Rio Tinto. Hello, Ian.
Hey, thanks, James. Hello, everyone. Welcome to the session.
Next, we have Paul Mansfield. He's a principal hydrogeologist with Vi Groundwater Solutions. Hello, Paul.
Hi, everybody.
Next, we have Gus Rowland. He's a principal hydrogeologist and country manager of South Africa at Patoa Associates, and it's very late there. So thanks for joining, Gus.
No problem. Thanks for having me.
And next we have Tyler Clough. He's a senior hydrogeologist with Patoa Associates. Hello, Tyler. Thanks for being here.
Nice to be here with you.
Okay, so just a little bit of housekeeping before we get started. If you're joining today, you are muted and your video is off, so no need to worry about any of that. If you'd like to ask a question, you can use the Q&A function at the bottom of your Zoom control panel. There is a Q&A function and a chat function. They look very similar. We encourage you to use both, but if you have a specific technical question, please use the Q&A function. It helps us make sure that we don't lose your questions. They can be anonymous as well if you choose. There's also an option to vote for other questions that you want answered, so we can kind of high grade them. This is also a recorded webinar. We'll post this to both the water course and our GCE YouTube page. So I think one of my co-hosts will go ahead and put a link to our YouTube page there. And just a quick disclaimer, I won't read it verbatim, but just know that this really is for educational purposes only. It's not intended to be professional advice. If you're having issues at your site, we encourage you to seek professional advice for your site-specific challenges. So this is the 5th webinar for the water and mining course. You can see the other topics in the blue there on the left. If you'd like to view any of those previous webinars, you can view them at our YouTube channel. In today's topic, we're going to be covering monitoring programs, performance assessment, interactive planning and risk management, and geotechnical hydrogeological guidelines for mine closure. So with that, let's go ahead and get started. So our first question for the panel. We have seen a lot of slope failures occur because of rainfall, and the course discusses the interaction between shallow pore pressure, slope dilation, and weathering along fracture zones. It's a two-part question. First part, how can some of these factors be measured in the pit? Second part, what is the best way to input transient pore pressure due to rainfall into our geotechnical model? So I'll go ahead and open this up to the panel.
Okay, I'll go first on this. Absolutely right. And, I think a very, very large amount of global instability is because of shallow groundwater infiltration and rainfall. So this question is spot on. Been dealing with 2 or 3 issues today, in fact, where all the analysis was done on deeper seated failures, and the failures are due to shallow conditions. So it's a very topical question. So how can some of these factors be measured? Well, I think more and more, and Jim Weigel can jump in on this, but more and more we're putting in, I think there's a couple of parts to it. Firstly, we're putting in piezometers very shallow. So a lot of sites we're putting in 50-meter holes and putting pressure sensors at 50, 40, 30, 20, 10 meters in the hole. So actually start to measure the way water goes through the shallow part of the slope. Those piezometers can be focused. Obviously, there's going to be some sectors of the pit which are more susceptible than others. So focus them where you think there's issues, but shallow piezometers. And then the other thing is horizontal drains, and particularly where we have fractures which are parallel to the slope. Horizontal drains and relatively shallow horizontal drains are often important, and they may not flow for most of the year. They may only flow during or following a rainfall or a snowmelt event, and that's when you need them. And you can actually think of them as like the pressure relief holes in like a retaining wall or a civil engineering structure. The same thing. They just flow when you have a buildup of pore pressure. And then the other thing is to put in some shallow horizontal piezometers, maybe not so shallow, but horizontal piezometers. Again, these can be drilled slightly downwards, put TDRs in with them to measure where the deformation is. So those are the 3 things that to measure in the pit. So holes with closely spaced piezometers, horizontal drains which aren't too deep and which target the dilated zones, and horizontal piezometers and TDRs. The second bullet, I actually just sent an email today to somebody saying the LOP needs to provide some guidance on this because there isn't any. Lauren Lorig did a paper at the last Slope Stability Conference, but it was a little bit numerical probably. And most people, the most common way of doing this now is to use an RU sensitivity. So even if you've got a free arc surface or if you've got a pore pressure model, you can put in RU values above that in what's in the zone above the phreatic surface. And you can vary the RU to a point where where if you've got a good kinematic analysis, you can vary the RU to the point where you can see where the instabilities occur, and then those are your focus areas in the pit. So keep increasing the RU, see where your instabilities are. Those become your focus areas, and those are also the areas to focus your surface water control. So that's a very good question, very topical question. Lots of instabilities because of this. So let somebody else have a go at that too.
Yeah.
Yeah. So
Go
Jeff,
ahead.
I was just going to quickly comment that, spot on as far as, I'm concerned from a Rio Tinto perspective, and I guess from everyone else as well. There is a temptation from sites that if a piezo is dry, to stop measuring it. And so, as hydros, we understand the processes. The geotechs have a different view of the world. They tend not to operate in a transient world. And so, for your site, you really need to maintain the monitoring right through. So if a piezo is dry, that's information in itself, and you need to ensure that your monitoring of that piezo just continues, and it's just not disregarded as a dead one. And the same probably goes for the drain flows. Again, the data is key. Measurement of flows, even just an anecdotal visual management of flows, if you can't physically get to a drain safely.
Yeah, the key here is educating your clients as well, and the operators of the mine, because you'll sometimes get some pushback when you're drilling drains 100 meters deep or whatever in length, and they're not giving you any flow. If you put in the vibrating wire piezometers before, and you demonstrate that during certain times of the year, for example, after the main recharge events due to snow melt or whatever, you're getting these increases in pressure, and the rest of the year the sensors are basically showing negative pressure. That helps you to explain why you need to put in some of these shallow horizontal drains to capture this shallow flow after these events. So it's key. You have to educate the people you're working with as well to get them on board with this.
Just to add to that, Paul, Blair here from BHP. We've had a number of failures related to this type of mechanism. Now, they're very difficult to measure in some cases. Actually, piezometers don't pick them up because you're looking at very localized recharge events, maybe through tension cracks, maybe through other geological features. So that first point about what can be measured, yes, we can put in piezometers and we can measure them through instruments, but I think there's also the need to make sure we understand the structural domains we're operating in and how these structures and their scale of them, where they could occur, and seek to look for things such as tension cracks which open up, and map them, understand them. There's a bit of back analysis as well that needs to be done here. And on that RU, yeah, Jeff, that's really the only option we've got, but it's a bit of an ugly parameter to use, the RU. It's really not that applicable in most cases where you have a little bit of complexity in the hydrogeology, and you're really just playing with a bit of a fudge factor between 0 and 1. So even though RU can be used, you still got to relate that back to some sort of hydrostatic condition. Yeah,
but it can actually, it can actually, by varying it can actually pinpoint where your susceptible parts of the slope are if you don't already know them. So I think that's the way we would use it. Yeah.
The one thing I would say too in RU is do the measurements, figure out what the variation in RU is across your sites. It might be drastically different between different sites. With all the shallow instruments that we do put in, we're able to calculate different RUs for different events at different time scales. So it gives us an idea of what our recharge response looks like in terms of an RU. So you're not just ranging numbers from 0 to 1.3 or 0.3, sorry. So basically grounded in observations whenever possible.
Yeah,
Jim, I think that's a good point as well, is that there's sometimes a tendency to use the sensitivity analysis of RU as kind of the end of the line and then not go back and look at it after the fact. And so using those observations to sense check what you've seen with your sensitivity analysis is important. And as Blair said, you want to make sure that you're linking that to real values and getting an understanding of how your RU relates to an actual pore pressure elevation or a phreatic surface.
And a really good practice is to have a set of hydrogeologic cross sections that include the piezometric data, but also all the secondary observational data about water as well. So the locations of wet blast holes and the locations of observed seasonal or permanent seeps in the pit slopes, for example, and the location of flowing horizontal drains. And often if you plot all of that information onto the cross section with the piezometer data, you'll find that there's a lot of water present above the main piezometric surface in the pit slope. And so you can then use that information to inform the geotechnical model about where there is perched or transient water, and to get some sense of what kind of ranges of RU to try and apply. And we've had some good success where we've been involved with FLAC models that have initially just been calibrated with the regional piezometric data and the deeper groundwater levels, and the deformations in the slope can't be replicated. But then when some RU factors are added in those areas that are defined as having transient water through mapping the wet blast holes and seepages and so on, when that is added into the models, then the deformations can become calibrated. So I think there are certainly, using that observational data and all the information to help inform the geotechnical analysis can produce some success.
All right. Very thorough answers on that one. Thank you all for that.
Yeah, good question and very, very topical. And it's right. Globally, a very, very large proportion of the instabilities occur because of this. These type of triggers.
Yeah.
Very good. Okay, great. Well, thank you for that. Let's move on to the next question here. This is also a two-part question. Sometimes when drilling vertical or inclined boreholes in the transition and fresh zones, the intercepted fractures cause drilling progress problems and equipment difficulties, and sometimes abandonment of the planned start point. Part 1, do you have an efficient drilling method or drilling fluid to maintain the wall of the desegregated zone? Part 2, what would you recommend to us to overcome these areas of disturbance, which constitute the main water flows? Again, I'll open this up to the panel.
Oh yeah, I'll give it a shot to start with. I mean, I think the reason back 20, 30 years ago, the reason the dual tube reverse circulation drilling method was kind of pushed was because of unstable holes. And the theory with it's obviously an exploration technique. Most holes are drilled 5.25 or 6.5. But the theory is that the drill pipe is a similar size to the bit. Most reverse circulation drill pipe is 4.5 or 5.5 outside diameter. And so, although the hole may become unstable, it can't cave because it's propped up by the drill pipe. So reverse circulation is a good way of doing this. Obviously, then the issue comes when you have to pull out and if the hole collapses. But a lot of times, if continued cleaning with RC or reverse circulation gets rid of the problem. If you're drilling wells and you have issues, then sometimes you have to go to case in advance or sonic. There's a number of ways to do it, and it depends what you're drilling. I mean, you may want to mud up the hole depending on what it's going to be used for. But the problem with mudding up the holes is you tend to there's a tendency to damage the fractures. So I think for the start, if it's an exploration type program or a groundwater investigation type program, go with reverse circulation. If it's a larger diameter well, there's a reverse circulation drilling method which keeps the fluid low in the hole. But if it's really unstable, you might have to go with case in advance or sonic.
I think for very high flow areas, we've seen good success with flooded reverse circulation. So kind of the opposite of the low flow idea is you want to keep your hole flooded as far as possible, but then using reverse circulation to prevent erosion of the sidewall. That tends to work really when you've got really high flow situations that you don't have to worry too much about mud caking your principal fractures of your primary water bearing zones. It's very slow and time consuming, quite expensive method, but sometimes it's one of the few ways you've got of getting through really, really unstable zones. Especially we found that in the base of deep weathering in high flow situations in sub-Saharan Africa, that's been quite effective.
So I was going to say, sometimes you're a bit limited by the gear you have. I have done projects in remote parts of the Philippines with an exploration rig, and impossible to get a hole through broken ground by conventional means. And we went to a casing advanced method, 8-inch casing. It was a big rig, but then used the old cable tool trick. So got the casing to TD, dropped a well screen inside the casing and pulled back to expose the screen. So it was an adaptation of the very old-fashioned percussion method of construction, with a rig that was really set up for just pretty much conventional rotary. So sometimes you have to adapt and work something out. Yeah, and not screw up the hole with bentonite.
Well, I was going to just chime in that in some cases we've had kind of good success with dual rotary, that method, and I've been surprised that the cost differential in some parts of the country is actually quite similar to RC drilling. So, and that again goes to supply and demand and the availability of the rigs. But if you are having that, I mean, that's something to think about and cost out with these advanced casing methods. Is some places they're available and not that expensive.
All right. Very good. We're done with that one. Let's move on to this question. I think is really interesting. Might not be super widely applicable, but very interesting nonetheless. In an Arctic environment, what types of in-pit monitoring can be used and what problems are caused by the cold weather? Do you have examples? How can we integrate groundwater and geotechnical monitoring? I'll open this up to the panel.
Again, I think vibrating wire piezometers are good in an Arctic environment because they're particularly the grouted in ones. I mean, the issue we used to have before the advent of the vibrating wire piezometers, we used to have problems with putting monitoring wells through the permafrost zone because they freeze, and we used to use all kinds of fluids in the observation wells to keep them open. But these days we can just put in vibrating wire piezometers, and they're also got temperature sensors on them, so they can use them to measure the temperature and the water pressure, and they can tell you when you're at the bottom of the permafrost. And so vibrating wire piezometers are probably the best way to go. I think most Arctic mines have them. Certainly all the ones I work at have got lots of vibrating wire piezometers installed. And again, they can be put in with TDRs, with shape arrays, with inclinometers in the same hole. The inclinometer may be an issue if the casing gets full of water and freezes, but if you go with a shape array or a TDR, then that gets rid of the problem. So yeah, I think these days the cold weather doesn't really give us too much of a problem with monitoring because we can grout the instruments in. It's a bit of a different issue with horizontal drains. Obviously, they freeze at the collar, but I think the question is specifically about monitoring. So, yeah, BWPs and grouted in geotechnical instruments.
Yeah. There is a problem with battery life in the cold.
That's
so
true.
You certainly need to be aware of that.
Yeah, that's true.
Which, yeah, maybe it's better battery technologies around that I'm aware of. But a Darvik, which is very much in the Arctic, we struggle with battery life on instrumentation.
Yeah.
And also with these solar panels, you've got on your telemetry, you've really got to be careful for low light.
Yeah. Yeah, I mean, Darvik has lots and lots of vibrating wire piezometers all around the pits. Yeah, so.
Yeah.
In terms of like integrating groundwater modeling and geotech monitoring, we'll put 2, sometimes 3 piezo's on an inclinometer pipe when we grout them in. Similar with the shape arrays, not a problem when you're actually constructing the hole. And then most of our groundwater piezos also go in with TDR cables and all get grouted in. So we have fairly good integration in terms of geotech and hydro here at Kennecott.
One of the things we found in a number of Arctic sites, and Darvik is one of them, is freeze back in the pit slopes. So we've had piezometers close behind the pit walls, which show declining temperatures at the point where it starts, where the slope starts to freeze again, particularly north and east facing slopes. And just knowing that can be important for the geotech analysis as well, because obviously if it freezes, then the strength will increase. So the great thing about the piezometers is you can measure both temperatures and pressures. But also if you got permafrost, there's probably no substitute for thermistor strings, because you can put a lot of thermistors in the string, and they can give you very good resolution on the permafrost zone and potential changes to the permafrost zone. So I guess the answer to the question is these days you can use a similar set of instruments to you would anywhere.
Very good. Interesting question. Thank you all. Okay. We've got another 2-part question here. I understand that cave mining can be affected by attenuation of water recharge in fragmented fine-grained layers above, and also faster short-circuit inflow from marginal fracture zones or relic structures. Part 1, I know it is difficult to predict flow, but what investigation methods can help? In Part 2, and once these features are identified, can you mitigate them? I'll open this up to the panel.
Yeah,
All
look,
right. Go ahead, go on, Blair.
I was just going to make a bit of a statement about it's very difficult for caves to predict inflows, but most of the time, my experience would be it's surface water related contributions that you need to understand. So you've got a water balance issue, trying to understand the propagation of structures and where they may penetrate to the surface and how it connects with surface water becomes the real key here. Notwithstanding, when you understand the surface water contributions, there's also the groundwater elements, which can be quite significant, particularly sub-level block caves where you haven't propagated to the surface. And obviously the vibrating wires drilling become extremely important, but so does the structural model. Nothing can be done in isolation. And I know we talk a lot about what we do as hydrogeologists, but really integrating hydrogeology into the geotech models and the structural models become imperative for caves, and using those structural models and developing them out to really know where you need to land vibrating wires, where you need to land instruments. It can't be guessed. It's got to be using some knowledge base, and that knowledge base is typically associated with the structural developments. And
yeah, I think that's 100%, Blair. I mean, I think, you know, much of the inflow to many cave zones is either surface or shallow groundwater. The other real thing that we're starting to realize with cave zone is the underground inflows are often directly below the point of recharge. So if you have, let's say, a crater zone with a accumulation of water in the bottom of the crater zone, then the inflows you see underground are often directly below the middle of the crater. And you know, and then there's other examples of where you have there's one example in Canada that we'll work on where the main source of inflow to the cave zone is water along two paleo channels, and all the wet panels and all the wet draw points are directly below where those paleo channels enter the cave zone. So you're right, it's very difficult to predict flow. It's very difficult to determine which structures are going to convey water. You can, I think that again, a good cave operation will monitor the free water, the moisture content, and the fine grained material of all its draw points. And so that then if you tie that back into the structural model, you can start to build up a picture of which structures may be important and which ones are not, and whether it's even structurally controlled at all. So as Blair says, focus on the surface monitoring at the top. Monitoring of the draw points is really good. There's not that many operations do it well, but many do. Just so free water, moisture content, fines grains content of all the draw points, and then it enables you to build up a picture, but very difficult to make precise predictions.
But if you do know there's structure underground, you can drill in advance too. So make sure you start introducing programs where you're drilling out in advance of where you're about to mine as well. So if you do think there's structure under there and it may be pressurized, as Jeff said, the deeper systems which are not connected to the cave during the early stages anyway, you need to find them, and waiting until you intersect them with a drive is dangerous in terms of just getting the right pumping equipment in there.
Yeah, I mean the three key ingredients for a mud rush are fine grained material, water, and uneven draw. And so I think most operations now will risk rank their draw points, and so there'll typically be higher risk draw points which are either mined more carefully or with remote equipment, and then there's lower risk draw points which are typically safe. But underground monitoring is key for this.
Oh, and one more thing, don't pretend you can model it. That would be my advice. Don't make sure there's not a groundwater model that you want to believe in, because it's just you're introducing a whole set of dynamics in terms of structural geology. Unless you've got that in there, it's going to be fairly unrepresentative.
Yeah. The other thing that really controls inflow is prior rainfall events and prior saturation. Your water will come through a lot quicker if it's going down flow pathways that are already saturated, and a lot of cave zones will find that early rainfall events in a wet season don't produce much water, and later ones do. And if you have back-to-back rainfall events, it's often that the first one hardly produces any water, and the second one, which can be smaller, produces a bunch of water. So pre-wetting of the flow paths is also important.
Yeah, that was very much the case we experienced at Argyle.
Yeah.
A mine pit that underground that wasn't originally designed as an underground had a sort of unacceptably large surface water catchment, and we knew by the end of the wet season that every time it rained, we're going to have a mud rush underground. Whereas the first 2 or 3 months of the wet season, not so much.
Yeah.
But yeah, that speaks back to the wet season aspect and also the surface water management. We certainly had a pit that, I guess, an underground that wasn't designed as an underground, so it had really poor, catchment control.
Yeah, wasn't a lot you could do about it at Argyle. No.
No. Well, we got all the waste dumps grading into the pit, right? And you got doesn't help where if you had, if we'd known in advance it would have gone underground, we would have, graded the dumps. Yeah, definitely.
Yeah. There is a paper on Argyle which was done by Toddy and myself in whenever it was, 2018, and a lot of people have referenced that, and I get quite a few questions about it. So it's on the Argyle predicted inflows in Argyle.
The second part of that question, Jeff's about mitigation, and I'm not sure if anybody wants to have a crack at that, but obviously if you start hitting large structures down underground and large water flows are in there, obviously you've got to get your pumping equipment that's capable to deal with it. But you also got to recognise the fact that you could have very high pressures. So when you're drilling through this stuff, you've got to be prepared for high pressures and the safety issues that come with that, and making sure you can seal in. If you are using drains, seal them in properly. Make sure that you've got control on them. I have seen packers used. I have seen grouting used to mitigate some of these larger structures and prevent inflows. But the reality is you just subside. You're just basically reducing inflows. You still got to deal with them and get the water out and get the right capacity. Not sure if anyone else has got ideas around mitigation of inflows.
No, I think predicting the pumping on a new cave zone is really difficult to predict what the inflow rates are going to be, and therefore, if you're a deep operation, you can spend a lot of money in a hurry on large pumping systems, and it's the same thing. You can back off on what you think you're going to need, and then you get a large rainfall event and you flood it out. So it's always, most people always go on the conservative side, but it is difficult. And I think one thing, as you say, is very difficult to predict this stuff. But as soon as you get surface breakthrough, you can actually start to see how the cave zone's performing. So when you break through from the surface and you've got a fairly small cave zone, that's the time to really increase your monitoring, so you can get a feel for what's going on. So when the cave zone gets bigger, you can understand it more.
The prediction is not just key on pumping system. There's impacts on ventilation, cooling, all that sort of stuff. As well. And it's a balance, right? You don't want to be so conservative that let's just sort of over design stuff, but equally so the consequences of a high humidity, hot mine, can't be understated.
All right, fantastic. Another very thorough answer. Thank you for that. I'll go to a live question here. Which drilling method would you recommend when drilling on a tailing storage facility embankment for installation of grouted vibrating wire piezometers, and why?
Probably, I'll take a crack for nobody else. Probably Sonic. I think there's a lot of discussion with some of the recent TSF instabilities about using any kind of fluid for drilling, not so much in the embankments, I guess, but in the tailings itself. But I think, if you're drilling TSF embankments and it's fairly coarse rockfill, it depends on what the embankment is, whether it's a sand dam or whether it's a rockfill dam. If it's a rockfill dam, probably Sonic. If it's a sand dam, you could it depends on the consequences, but a lot of people will drill a sand dam with reverse circulation, but keeping careful control on the fluid loss. But you know, some tailings impoundments or some operators won't let you drill at all with fluid in a tailings impoundment because of the risk of increasing the pore pressure, and that applies to air as well. The air can, if air gets into the unsaturated zone, it can also create pore pressure issues. So I think the safest is often sonic.
All right. Very good. Any other thoughts on that?
Yeah, I mean, if it's a rock dam, and you assume you're putting the piezometer in a drainage blanket or something like that, you won't get any return of your grout. So you just need to be aware of how the holes get cased above the a drainage blanket or a filter that you're trying to monitor.
Yeah.
So be aware of that. You certainly won't get any return through a rock fill dam.
You won't. There's a number of ways of doing it. You can put filters in. We've been putting in VWPs, and Jeremy may explain it, but we've been putting in VWPs in leach pads and dump leaches with variable success. But you can again put in lots of lost circulation material to plug up the sides of the holes. But again, you gotta look at if there is any implications of losing a fluid loss in a dam. That's always something to consider.
All right. Blair, did you have another thought on that? So
I was just going to say we do a lot of work on tailings dams, so the heightened anxiety across the world at the moment. I've never really come across that argument about injecting too much water into the formation or fluids. I know it's there, but the reality is, you've got to put a fair bit of pressure in the system to make it fail. If that's the introduction of drilling mud does that, then you've got serious issues. So I'm assuming you're on a facility where you're trying to understand, and you're putting vibrating wires in to understand and get some monitoring in there, so you can maybe set some TARPs, trigger action response plans. Therefore, I think the drilling method needs to recover sample. You need to understand to make sure you can correlate where you want to land your vibrating wire with the condition that you're looking for. Because if you are looking for some moisture zone down there, you really make sure you need to find a drilling method that allows you to look at that and couple it with geophysics. So whether it's sonic or whether it's just traditional coring, really depends on the sensitivity of those pressures, as Jeff said. But I think generally the coring methodology, if you can get good recoveries of samples, is also still useful, because not everyone's got a sonic rig in their back pocket that they can just bring out to site. And they are a bit more expensive. They do get held up on rock if it rocks down there.
Yeah, I think particularly if you're in a sand dam, I think dual tube or triple tube core is good. And it's an interesting one, about fluid loss. I mean, as you probably well know, there's theories that there have been tailings dams instabilities caused by drilling, and you can argue one way or the other. But there's 3 or 4 tailings facilities that I work at where it's any drilling with fluid is well, not allowed.
I guess that's after Brobandina and things like that, isn't it?
Yeah, exactly. Yeah, exactly. Yeah.
I mean, the other thing is with your drilling methods, you need to make sure you've got control of your hole. If you're drilling into a foundation that's got some pressure on it over rock fill, you won't actually see that you've drilled into a pressurized foundation. Yeah, so you need to be able to. You'll lose it at the transition under your confining layer. So you really need to be sure when you drill in, you are doing your full risk assessment. What happens if we can't seal this up? How do we get the instrument in that is providing us with confident data, that sort of stuff. Yeah, and it could be case to the top of case 3 rock fill, for example. seep, seep encased in through rock fill.
Okay, great. Thank you all. Lots of considerations there. Okay, let's move on. Got a question here. This is about mine closure. Is it required or common practice to cement drain holes or wells at active closure stage? If not, what would be the risk of it inducing transfer of chemistry across aquifers and surface water? Good question.
I think I'll give a quick comment there. I think the most common implication of not cementing exploration holes is certainly if you decide to build an underground mine in future, you risk inducing flow to your underground operation. This is something that's quite common in Southern Africa with underground mines that are being planned and excavated beneath old open pits that were never envisaged. And so you're getting a lot of intersection of underground, open exploration holes that bring flow through from shallow aquifers through to the underground operation. I can't comment much about grouting wells per se. And the risk as far as underground mining goes tends to more be about the quantity of water than the chemistry of water. But in situations like this, we have seen some interaction of nitrate-laden shallow groundwater that is then interacting with deeper, better quality groundwater through ungrouted exploration wells. Again, grouting those wells straight after exploration tends to be the best way to deal with that. Once you've moved a rig off and once you've left a hole open for long enough, you're almost certainly not going to be able to grout it after the fact.
I think sometimes there tends to be corners cut with this because you have to remember every time you put in an exploration borehole, you are potentially connecting two sets of aquifers or you're providing a conduit for surface water to get into your system. So you really should be looking at cementing it up. I mean, obviously it depends on the project and depends on the closure plan, etc. But yeah, often people forget about exploration with the holes until it's too late.
Yeah, we have
I
a scenario here at Kennecott, and Tyler can talk to a little bit about it, but there's this old working called NOS, the North Horseshoe Shaft, and they brought in some exploration drives. And while they were doing the exploration, they're putting in all sorts of core holes to investigate the ore body. Eventually, due to economics, they closed that, and also just the amount of water they were getting into that drive, they ended up closing it off. But part of the reason they were getting all the water is they effectively created a drainage gallery within that exploration drive. And so now we're reliving that a little bit, and Tyler gets to model a lot of that for us, come up with methods to deal with it. But yeah, so there are some things that can happen from that. The other thing too, I think when you start going in and talking about closure and whether you should, abandon all these, I think in general, it's a good idea, but the bigger question is, what are the potential impacts and what is the hydrogeology at your site location? Are you in an area where your current mine is a aquifer recharge area? If that's the case, then absolutely it's going to have huge implications to downstream groundwater users. If you're at the end of the pipe where you're basically at a basin, the end of a basin, then maybe it doesn't have as much risk for closure. So I think you just have to understand where you are in the hydrogeologic cycle and what the downstream risk factors might be.
And Jim, I mean, it sounds like particularly you're talking about if you're in an open pit in a pit lake environment, whether that becomes a flow through or a sink, right? And then what the downstream implications are from a chemistry standpoint, or if you start bridging hydrogeologic regimes with drain holes or drill holes.
Yeah,
and just sorry,
go ahead.
I was just going to say, from a practical point of view, I mean, realistically, you can't cement up drain holes, right? They're up on the benches you can't access. You're not going to get access to even the drains on the lower benches to drain them, and then the consequences, right? So you're going to, the drains are there for a reason, to maintain pit stability, and it's incongruous really to grout them up while there's still activities happening in the floor of the pit on closure. The other thing, of course, Jeff's going to say, wells, no open wells. You put a
or
piezometer
vertical
in every well.
drains too, for that matter. There are some places in Nevada where they're actively draining the pit by drilling into something that has no water or much lower pressure heads. So essentially transferring water between different geologic units. So in those cases, it might be prudent to grout up those drain holes if possible.
Absolutely. Well, that comes back to the connectivity.
But in some of those, sorry, Jeff, go ahead.
Go on, Tyler.
Just in some of those cases, you've already connected those units just by virtue of the open pit there. I mean, a lot of those settings where you're doing the vertical drains and the dual aquifers, I mean, the pit is or shaft, whatever it may be, has already bypassed those. And so it just, it kind of comes back to, I think, getting your head wrapped around that conceptual setting and understanding it.
Yeah, but I mean, there is a requirement in Nevada and several other Western US states to do it, which, as you say, is crazy. Operators find themselves grouting up holes and wells which are in rock. You've got a 10-inch well, and you've got a 2-mile wide pit next to each other. It doesn't make sense to grout up the 2-inch, the 10-inch well, but the regulations kind of say you've got to do it. So you either do it or you obtain a waiver. But I mean, I think just thinking about closure, it depends on the situation. I mean, if it's never good practice to cross connect groundwater units. So if you are drilling through 2 different units and there is going to be a vertical gradient, you should probably cement them up. But if you're just drilling through hard rock and it's all going to equalize upon closure, then maybe you don't need to. So it is as for most things, it's a case by case situation. But I think, to answer the question, there is a legal requirement to do so in certainly in several other Western US states. So yeah.
All right. Very interesting question. Interesting answer there. Thank you for that. Okay, let's move on. Would you mind talking of water disposal options and how it is integrated on dewatering operations on the overall water balance, specifically the implications of monitoring and development in terms of permitting and engineering process? Open this up.
All right, I mean, I'll give it a go. So water disposal options for dewatering systems, you can try and list them. So there's discharge to surface water, sometimes with treatment, discharge to wetlands areas, rapid infiltration back to shallow groundwater systems, deep well injection to deeper groundwater systems, surface evaporation in drier areas. So there's a number of options, and it depends on the overall water balance, of course. Does the site need additional water, or does the site need the water for mineral processing, or has the site got enough water for mineral processing and needs to get rid of the water? And if it's it depends on the environment you're in, but if you're in an area where you've got lots of clean water, then and you have to treat the discharge, prior to discharging it either to groundwater or to surface water, then it becomes it can become a very expensive operation, and the cost of discharging the water can be actually greater than, in some places, greater than the cost of pumping it. So it's fundamental to integrate the dewatering system in the water balance, and it's if you've got excess water, then potentially if you've got excess water with that is not the best quality or has some elevated parameters, then the water balance circuit sometimes needs to be set up to get rid of the water on site by evaporation sprays, road watering, so on and so on. So yeah, and then other cases, if you've got a dewatering system with which you're pumping clean water, maybe you've got good interceptor wells, and the water quality meets discharge standards, then you can quite happily pump it and put it back to the environment. Yeah, there's lots of options on this, and so it really comes down to understanding the water balance and understanding the flows and understanding the chemistry and deciding whether you can discharge it to surface water, groundwater, and what the engineering and treatment implications are.
It's actually really important as part of the dewatering planning process to understand what the end use or the final customer for the dewatering flows is going to be. And we work on 2 or 3 projects that I can think of where the dewatering flow rates and the actual ability to dewater the mining operations is limited by the lack of water disposal options at the site, which may be due to permitting constraints or even just having a social license to discharge water from the site. So the ability to discharge the water is really key in the dewatering planning and can be a significant constraint on the ability to execute a good dewatering program.
Just to build on that, Jeremy, you've got there's a really important piece here, which I think the question is alluding to, which is around uncertainty. They're intrinsically linked between dewatering and excess water management. And so the uncertainty you have with dewatering needs to transfer to the uncertainty that you need to consider with managing that variability. And I looked at Ian and our BHP and Rio both had massive problems challenged with dealing with excess water in the Pilbara, large volumes. But you're absolutely right that dewatering is constrained in some cases. But I think the good planning, long way out, and people understanding that uncertainty that we know in dewatering rates needs to also be considered in the uncertainty with the solutions that you look for and the permitting that you are seeking, so you don't constrain your dewatering, you have flexibility. But far too often, surplus water options become quickly overwhelmed, and then you're limited. Then you're in a reactive position. You're no longer proactive, and so being able to have that flexibility is good, but it comes at a cost. So therefore, there's an economic trade-off here to say how much flexibility do we want in our surplus water account for variability that we have, not only in the hydrogeology uncertainty, but the mine planning uncertainty, because the mine plans can change. And so if mine plans want to change because there's higher grade ore, they have an opportunity to sell at the market, they'll want to pump more, and pump more means they need to dispose more.
Yeah, there's a couple of things here. So the chemistry that Jeff mentioned, so there's a stewardship aspect, right? So which is underpinned by using the worst quality water for the first, and so that is absolutely a consideration from an engineering process, and that allows obviously has flow on effects with with the ability to discharge or re-inject or whatever. The other thing, of course, is sustainability. If you have a discharge mechanism that's providing irrigation water to a farming community, what have you, there is that social aspect where people have built an industry or a dependency on the discharge water, which has a finite life, and so that absolutely needs to be a consideration as well. And then, of course, the cumulative effects. If you've got multiple mines in the same catchment, which is what we see with in the Pilbara as well. So yeah, tricky if you've got too much water. Yeah.
There's a solution there, isn't there, to work with each other, though, isn't there? Like,
that's right.
to broader than hydrogeology, you start talking about mining companies having to connect and work together and find mutual solutions with sustainable solutions.
Yeah.
So on the flip side, there are a number of mine operations who are short of water and try and encourage you to pump as much as you can out of the dewatering system. And there's a number of countries where the permitting is less onerous if you can prove you need to pump the water for dewatering. Whereas if you need to pump it for water supply, you have to permit it. So there's a number of countries where it's an incentive to pump as much as you can for the dewatering to provide water supply. And so there is the flip side of the story.
Like here in South America, I think most mining operations would be quite pleased if they had excess water in their operation to use, because there's quite a shortage of water in most of the areas where we work in one of the driest deserts in the world, in the Atacama Desert. They don't get that luxury.
Yeah, and I mean, I don't know whether it's still the case, Paul, but there used to be Chile is one of the countries where you didn't need to permit water if it was in the way of mining.
No, that's right. It's still under the mining code as water found in your operation you can just use and you don't need to permit. So it's changing, but it's still the case.
Yeah, there was a number of operations that we used to work on where we tried to maximize the amount we could pump, right, just to provide water supply.
Yeah, absolutely. They're still trying to do that in some operations today.
Yeah.
I think that design component in linking the water balance and sustainability, Jeff, what you were just mentioning, I just reiterate, I'm working on a site where the same sites with their current plan is going to experience both a water surplus and a deficit inside of a 7-8 year period, and an element of that is because of an over aggressive dewatering program. Dewater everything all at once, way ahead of time, and now you're in a water deficit, and you're pulling fresh water. Perhaps it's unneeded. So, just highlighting, it's not one answer fits all, but really finding that link and that balance.
Yeah, actually, Tyler, that brings something to mind as well with a client we've got at the moment, and the saying that if you're not measuring it, you can't be managing it. Is really what that triggers, because so often sites don't necessarily know exactly how much they're disposing or exactly what the quality of that disposal water is. But more importantly, they don't necessarily know how much they're using in any great detail, or even if they have opportunities to use worse quality water than they are. And so making sure that from the very beginning, you're encouraging flow monitoring, flow measurement, quality measurement at every stage of the process, and making that a completely integral part of managing the system is really important. So that's where that monitoring comes in. You can't understand the system if you don't know exactly where the water's going and what it looks like when it gets there and where it comes from.
All right. Very good points. Okay, good question too. I think we have another live question here. Let's go to that. Okay. I've observed many times piezometer sensors installed at different depths within a single borehole registering different water elevations. What does this mean? Is it representing perched water tables or something to do with the sensors? I think this is probably a common question. So I'll open this up to the floor.
Well, I guess this depends, obviously. I mean, if this is a grouted in piezometer, then you'd expect to see potentially different pore pressures at different depths. I assume it's a grouted in piezometer. That's part of the reason why you grout in vibrating wire piezometers, so you can measure pore pressures across structures or other controls at depth within the same borehole. So it's representing the pore pressure at a particular depth or in a particular structure or in a particular block. So it would be normal to see that if you're talking about vibrating wire for sensors in a grouted borehole.
Yeah, Paul, you hit the
totally.
nail on the head.
Yeah.
Sorry, Jeff.
Well, I was going to say all mine sites have strong vertical gradients and mostly downward vertical gradients. And in fact, a lot of mine sites have larger vertical head gradients than lateral head gradients, which is why it's often preferable to use cross sections so you can look at the vertical gradients rather than maps where you can't. So this is an absolutely normal situation. And in fact, if you didn't get a vertical gradient, you'd be wondering why not. You'd be questioning the sensors if you didn't get a vertical gradient.
It'd be strange
100%.
to have the same pressures or the same water phreatic level. Well, it wouldn't be phreatic level, piezometric level in all the sensors. You'd probably question whether the sensors are grouted in properly.
Yeah, exactly.
Yeah, it's always important to go back to the rock and make sure that you understand what the sensors are installed in. Look at the lithologies, the structures, as Paul mentioned, and making sure you're understanding whether there's any difference in terms of weathering zones, transition zones, fresh fractured rock, and those sorts of things, and use that to build your conceptual understanding of why you might be seeing a different pressure gradient. But yeah, as Jeff and Paul have mentioned, it's absolutely common to see vertical pressure gradients. It's especially very common in areas with deep weathering in sub-Saharan Africa. We see quite often variable desaturation between the weathered zone, the transition zone, and the deep fractured aquifers. They can be connected, and so if you have open hole piezo's, you tend to have a single composite water level. But when you're differentiating between them using grouted sensors, you're able to see the differences between how the deep fractured aquifer might drain faster, for example, or the transition zone might drain faster than the overlying weathered aquifer. Even though they're still fundamentally connected, they do behave differently on different timescales.
One of the reasons that the vibrating wire piezometers became the norm in terms of pore pressure monitoring, especially here in Chile in the early 2000s, was because in some of the northern open pits in Chile, in very low permeability environments, open holes or standpipe piezometers were just not able to record representative phreatic level in a reasonable period of time, because they were so slow in recovering the levels after the drilling, and therefore it was very difficult to get any representative phreatic levels. And that was part of the reason why we started to install vibrating wire piezometers in some of the open pits, for example, Chuquicamata in the north of Chile in the early part of the century. And since then, we've never looked back. And the vibrating wire piezometers are now the norm in all big, medium-sized and big pits in Chile and throughout the world.
One way to consider looking at, a simple way to look at pore pressures in a profile, though, is to look at the HU coefficient to give you some idea of, is it vertically downward or upward? And that is where you plot the depth of sensor from the surface against the pore pressure. And that's essentially a hydrostatic line that runs through the middle of it. And with that, you can see where for each sensor, where they sit in relation to hydrostatic. And obviously, if you've got hydrostatic conditions, they'll all sit across along the line of best fit. If they sit below the line, you've got downward gradients. If the probes are sitting on the upside of the line, it's typically showing vertically upward gradients instead of downward, and pressure conditions. So there's different ways to look at the monitoring data to get a sense of, is it actually representative, and how you may want to then correlate it back to what Gus was talking about with geological units.
All right. Thank you all for that, and thanks for the question. Really, really good question. I think it's one that's commonly asked. I'll note that Ian had to drop off for some other obligations, so I want to thank him for his time. And it looks like we have another live question here. Let's go to that. This is from Mauro. Thank you for the question. It's a three-parter, so I'll go ahead and read through all of it, and then we'll kind of chip away at it. In co-disposal projects for tailings on existing waste rock dumps, we can assume that there will be changes in the hydrogeological behavior of the dump. First question, what would you recommend for establishing an investigation plan for the new conditions in co-disposal scenarios? Part 2, do you think there would be complications with the subdrain design of the original dumps? And part 3, how could we evaluate the changes in the groundwater recharge for deep hydrogeological systems if that happens? Thanks for the question, Mauro.
You want me to have a go? Hey, Mauro, hope you're okay. Co's disposal, it depends very much on how you do it. Whether you've got a low solids tailings or whether you've got a thickened tailings. If you've got a thickened tailings, there's obviously less need to be concerned about the water. If you've got a low solids tailings where you're running, let's say 40% solids, some people actually put liners onto beneath that. There's a number of tailings impoundments been put into waste dumps with line facilities. But if you're going to put a low solids tailings onto a dump, you've got to be really careful because you've got then release of water into the dump. And so that potentially, firstly, may have affect the stability of the dump. It may, as you say, give more water at the toe that you have to deal with, and it may give more downward infiltration. So I'm assuming the question is that you're looking at putting a low solids tailings onto a dump without a liner. There's not that much precedent for that, I don't think. And so yeah, first thing would be to establish the pore pressure conditions in the dump, particularly look at any layering within the dump, and then to do some initial water balance calculations as to what the release rate of water is from the tailings, and have some indication on how that may influence dump stability. So again, it's really firstly you've got to understand the dump. Put in piezometers if you can, put in vibrating wires or standpipes, and multi-level standpipes maybe the way to go, because you can sample them as well. An issue is if you've got many dumps are layered, and many dumps have old running surfaces which allow perch water to accumulate, and there's been a number of dump failures on intermediate lifts caused by perch water on old truck running surfaces. So that's an issue. So that needs to be thought through as well. So it's really figuring out what your pore pressures are, what they will be, and trying to do an early estimate of how much water may release from the tailings and where it may go. Not much precedent for there's a lot of precedent for putting filtered tailings or high solids tailings onto the dump, but not so much precedent for putting in low solids tailings onto a dump. Or if there is, they're lined. So I'm not sure whether the situation you've got is for high solids or low solids.
Just to add to that, Jeff, I'm not sure what the subdrain design is, but if you've got fairly wet tailings, let's say somewhere like 60%, and they're free draining, you may find that if the drain's not designed adequately, you'll block it pretty quick.
Yeah.
because of differential in grain size between the waste dump and the tailings.
Yeah. So it's something, you know, if it's a low solids tailings, you definitely need to be careful with it.
All right. Thank you for the question, Mauro. Much appreciated. Okay, let's move to this next question. We've got about 14 minutes left. Could you please comment on how to effectively include climate change factors, for example, extreme rainfall, in a water risk management program for tailings dam, in-pit tailings, and waste rock dumps? And what additional recommendations do you have to improve TARPs related to extreme rainfall events? Interesting question.
All right. Anybody want to go at this, or shall I give it a go?
Well, GISTM sets out some guidelines on this, the global standard for tailings in particular. And depending what stage of your development at, you know, it could be a 1 in 10,000 year event or a PMP. Putting a climate change around those numbers is enormously difficult. Increases cost significantly, but it's industry standard at the moment to close the site. I think for a tailings facility in particular, it's a 1 in 10,000 year event.
It is, yeah.
Correct me if I'm wrong, which is enormous if you've got a spillway that you've got to design. So I think there's a risk-based component here that, you know, during operations, you've got to be prepared to take risk, and we probably see at tailings at the moment, we over-design everything because we don't want to have an event, because it's catastrophic to the companies, because just social standing would be intolerable. So I'm not sure there's much ways to get around it. There are, you know, there's obviously a lot of work being done on climate change to look at the range of possible climatic conditions that we may see in the mid to long term, whether it's becoming wet or dry. And you can, based on where you're located, access that information. You may have to do a little bit of work around it, but that can give you some sense of how much increase or decrease it would be, and you can build it into your PMPs or your maximum rainfall events. I don't know, anything else to add?
Well, I mean, as for the previous question on code disposal, there's two parts to it, right? There's one, the stability aspects, the whether the change in water pressure is gonna affect the stability, and you know the way to look at that is to understand what the failure mechanisms may be for the tailings dams or the dumps, and it's normally related to the down gradient toes of the facilities, although not always. So make sure that, again, the implications of higher infiltration is understood in terms of what it may do for pore pressures along the critical failure surfaces. That's less of an issue for in-pit tailings. I mean, it depends. If it's purely an in-pit tailings, there's typically very few geotechnical concerns. There's potentially no credible failure mechanisms for some in-pit tailings, so the stability is less of a concern. But certainly you need to look at what the failure mechanisms are, where pore pressure is important, and make sure you understand the implications of any climate change on those, and set your TARPs is a conservative to a conservative level. In terms of the environmental side, again, with extreme rainfall, potentially you can. I mean, the main risk of it is actually erosion rather than additional infiltration, and so it's designing the surface water infrastructure to cater for it. And as Blair said, if you have you know, if there's no substitute for over design, because most times you'll find that if there is a failure, it's because of poor maintenance, not because of design, and the beauty about over design, it provides conservatism for when the maintenance isn't done or isn't done in a timely manner. If you've over designed the system, then the maintenance can be somewhat less important. So if it, I mean, the main thing with climate change is more related to erosion than groundwater. Although it is, you'd have to consider increased infiltration and increased groundwater.
The in-pit one, though, is interesting, isn't it, Jeff? Because we are looking for tailings deposition. You need consolidation, and whether that and whether you're getting under drainage is important. Because if you're not getting any outflow of the system vertically downward into the groundwater system, in-pit tailings will then remain, saturated. And although that's probably not problematic from maybe it's an environmental component, yes. Stability, probably not. But there's human health and safety factors long term about having a pit full of sloppy tailings that's not draining.
There's a couple of things with in-pit tailings. I'm just going to plug my laptop in here. Firstly, firstly, as you say, there's no under drain, and so you end up with typically with a lower solids content. And secondly, it's the rise in tailings is the rise in the tailings level is typically greater for an in-pit tailings, depending on how big the pit is, but it can be greater than for an in-pit tailings than conventional tailings. So the buildup of excess pressure can be larger. So you end up with you can end up with a tailing surface in the pit, which takes a long time to get access to. It takes a long time to consolidate. So but if the tailings is contained within the pit, then often there is no. It's purely a risk thing in terms of access. There's often no credible mechanism for release of that tailings.
Yeah, I agree.
And on the
with
top,
oh, sorry. Yeah, I was just going to say I entirely agree with Jeff's comment about one of the main issues being erosion and also sediment control, and in particular in the southwest part of the US, the main challenge that has been experienced in recent years is that even if the annual average rainfall is normal or even below normal, the intensity of the biggest storms is much greater. And even if the 1 in 100-year storm is still the same amount of rain over a 24-hour period, the concentration of the intense period of rainfall is becoming much more intense, and so the same statistically generated storms are creating much more severe storm events and aggressive erosion and problems with really the peak flow and the destructiveness of the peak flow related to erosion and sediment control. So that's really a critical issue, even in climates where the climate change may produce lower average rainfall conditions over long periods of time.
So to Jeremy's point on that, looking at some of these like basin designs for surface water flows, we kind of had the chance to look at some of these climate change scenarios. And in the Western US, these atmospheric rivers that seem to occur a bit more frequently, tend to string together maybe a 1 in 25-year event or a 1 in 50-year event. But the rub is that you get 3 of them in a row, back to back to back, like 3 days worth of it in a row. And the cumulative effect of those in a row had a bit more of an effect than a 1 in 100 year event, which would be the standard design criteria, or 1 in 500 year event. So I think that element of not only just what magnitude are these designs and tarps built towards, but what could be the effect of the frequency of a lower magnitude, but those occurring in quick succession is something to think about, right?
Yeah, exactly. It's not always about the extreme event. Yeah.
It's about an unacceptable event, and your tarps related to those unacceptable events, and that's your risk tolerance, because rainfall is inherently probabilistic currently. But I'm not sure what the question talks about tarps here, because there's only a limited number of things you can do when you get big rainfall events, and if the designs aren't in place to manage overflow, because overtopping with the rainfall events is the major core failure for a tailings dam. Yes, you can get rising pressures, that's a bit delayed, but it's overtopping. So what's the TARP here? It's basically making sure that those facilities are well managed and maintained, so overtopping and spillways work and operate. If you're relying on pumps to deal with getting water off the surface, then I think there's some design considerations that need to be brought back into it. So if you've got tarps linked and need to turn this pump on, but if you've got tarps around stop discharging tailings to the facility during these rainfall events, because you don't want to add any more water, then I think that's probably a reasonable one to start thinking through based on your risk tolerance.
Yeah, storage and spill capacity.
Yeah.
There is some decent guideline provided in the ICMM, the International Council for Mining and Metals Water Stewardship Guidelines, and the IRMA, IRMA, International Responsible Mining Assurance, the Institute for Responsible Mining Assurance Guidelines for water use on how to assess climate change. But most importantly, it's very region specific. And everybody's mentioned here that locations aren't going to all be behaving the same. Some locations are going to be getting drier, some are going to be getting wetter, some are simultaneously going to get less overall rainfall, but more extreme events. And so it's really important to understand specifically how your site is going to be affected by climate change. There is no one size fits all way to assess climate change impacts. It does have to be specific for your site and your region.
When the new LLP closure book comes out, there's quite a decent discussion on climate change in that. So,
Okay, well, thank you all. I think we're just at about time. It's a great discussion. I want to just briefly mention that today's webinar was based on our water and mine operations and slope stability course, which if you'd like to learn more about, you can scan the QR code there. You can also visit our website to see our other courses, which is mining.arizona.edu/GCE. Someone could put that in the chat. I would appreciate that. Actually next week, we will be releasing our newest course, which is this one, Fundamentals of Open Pit Slope Design. So a week from today. So be sure to check that out. And with that, I want to give another thank you to our panelists and our participants today. Our panelists, we really appreciate your time. Some of you are turning in quite late and you're all very busy. So we really appreciate your time and your expertise. So thank you all. And I hope everyone has a great day or night.
thank you.
Thank you, everyone.
Hope everybody enjoyed it.
Thanks.
Thank you. See you later.
Thanks.
Right.
All right.
Thanks all.
Bye.
Good
See ya.
discussions all around. Thank you.